In this example, we want to review concepts from the statics course that form the basis for this course on structural analysis. So we're going to analyze a determinate frame to find support reactions. The key concepts we're going to use are dividing structures into members and applying the equations of equilibrium. Here's our problem. It's a frame with vertical loads and horizontal loads, and we're going to determine the reactions it supports A and D. We're going to note that point A is fixed and points B, C, and D are all pins. And here's the approach we're going to follow. First, we're going to approximate the solution. And we're going to see how that helps us compare answers at the end and what we can learn from that process about our understanding of the behavior of the frame. Then we'll divide the structure into members. And we'll confirm that it's determinate. Then we'll apply equilibrium to each piece. And finally, we'll compare our answers with the approximation. Step 1. We're going to approximate the solution. We're going to assume each horizontal reaction shares equally. Well, if that's the case, all we need to know is what's the total horizontal force applied, 0.8 kips per foot times 15 feet, 12 kips. So we'll approximate AX as 6 kips to the left, and DX as 6 kips to the left. Next assumption we're going to make is that the structure can actually be approximated as a box sitting on 2 short legs. Structure. So it would behave solid trying to rotate. If we make that assumption, in some moments, we'll go about point A, well, we're going to get the 12 kips horizontal force acting through a height of 15 over 2 feet. We're going to have the 6 kips acting through 8 feet, the 3 kips acting through 16 feet, and dy acting through 24 feet. that together, and dy equals about 7 3/4 kips, acting up. And we'll sum forces in the y. Ay minus the 6 kips minus the 3 kips plus the 7 3/4 kips. Ay is approximately 1.25 kips up. Now these are very crude assumptions. If they are reasonable assumptions, then these will predict our answer fairly closely. If these are not great assumptions, then all we're going to be able to get is an order of magnitude estimate of the solution. And that's something we'll have to evaluate when we get to the end. I want to point out these assumptions ignore things like the moment resistance at A, the pins at the other connections. So we'll have to see how close we get with this approximation. Now step 2. Divide the structure. We'll cut it at each of the pins and away from the supports. So we have the left member AB, middle member BC, and the right member CD. A is fixed, so we get 2 force reactions, AY and AX, and a moment reaction, MA. D is pinned, so we get 2 force reactions, dx and dy. And then in each of the internal pins, we get 2 internal forces, bx and by. Newton's third law says that these are equal and opposite on the different sides of the cut. Cy and Cx. Now step 3. Confirm determinacy. We want to make sure that this is a statically determinate structure. Unknown reactive forces: 3, 5, 7, 9. Our number of free bodies: 1, 2, 3. So we compare 9, 3 times 3, they are equal. It's determinate. Now we need to check the reactions to make sure it's stable. They're not all parallel. Good. And they're not all concurrent. Good. So our assessment is correct. It's a determinate truss, or a determinate frame, and we can proceed with the analysis. Step 4. Apply equilibrium. Let's begin with member CD. It's 15 feet tall. Got vertical reactions dy, horizontal reaction dx. You have the forces at the cut, cx and cy. Let's sum moments about point D. We get cx through 15 feet, and that's it. So Cx must equal 0. Now we should have recognized that. There are no forces applied between C and D. The member is pinned at both ends. It's a two-force member, which means that the only internal force acts along the path of CD. So Cx and Dx have to be 0. And horizontal equilibrium would demonstrate that. Now let's sum forces in the y. I get a dy minus a cy, so I get dy is cy. They have equal magnitudes and our arrows show they're in opposite directions. Now let's move to member BC. We have point force of 6 kips, 8 feet from the left, and we have an 8-foot spacing until we get to 3 kip load. We have our vertical force at the end, Cy. Here we found that Cx is 0 already. We have Bx on this end and By. So let's start by summing moments about point B. We'll go counterclockwise. So the 6 kips acting through 8 feet, 3 kips acting through 16 feet, and Cy acting through 24 feet. Put all of that together, Cy is 4 kips in the direction shown. Now that we have Cy, we can come back to our result from member CD and see that dy is a positive 4 kips, which means it is a vertical reaction up. Now let's come back and apply vertical equilibrium to member BC. We'll take up as positive. We have By minus the 6 kip applied load, minus the 3 kip applied load, plus the 4 kip Cy that we had calculated just a moment ago. Put those together, By is a positive 5 kips, so it is in the direction we drew it. Now let's sum forces in the x direction. This time I'm going to go left as positive. It's my choice, and I think this will make it simpler. Has to equal 0. And all we have is Bx, so Bx is 0. Now we move to member AB. It's 15 feet tall. We have uniform distributed load on the side of 0.8 kips per linear foot. We already calculated that there is 5 kips down, no horizontal force there. It's fixed at A, so we have an AY, AX, and a moment about A. So let's start by summing forces in the x direction. Again, I'm going to choose left as positive because I think that'll make things a little simpler. We have AX, we have minus the 0.8 kips per foot times the 15 feet over which it acts. Those are the only horizontal contributions. So AX is 12 kips to the left. Now let's sum forces in the y. We'll choose up as positive. AY minus 5 kips up at B. And so AY is a positive 5 kips. Its reaction is up. Now let's sum moments. This time I want to go clockwise as positive. Again, it's my choice, and I think this will make it a little easier. So I have the moment reaction at A plus the 0.8 kips per foot times the 15 feet times the distance through which it acts, which is halfway up, 15 over 2 feet. Those are the only contributors to moment about A. So MA is not in the direction we drew it. 90 foot kips. But the direction we drew it was clockwise positive. Step 5. We want to compare our answers with the approximation we made at the beginning. That'll help give us confidence that the lengthy calculations we performed are reasonably accurate. So, what reactions did we calculate? We got a dy 4 kips up, a dx of 0 kips, an ax of 12 kips to the left, an ay of 5 kips up, and our moment reaction at A was not clockwise like we drew it, but counterclockwise, 90 foot kips. So how did that compare to our approximation? Our approximation had dy at 7 3/4 kips, our ay at 1 1/4 kips, our ax at 6 kips, and our dx at 6 kips. So what does that tell me? Our order of magnitude checks out. That gives me some confidence in these numbers. But the distribution of our reactions is very different from the approximation. And the question is why? Either we've made a mistake along the way, or some of the assumptions we made were not great, and so all we can get is an order of magnitude check from our approximation. So what assumptions did we make? We neglected to consider all of the following. The moment reaction at A, which will have an effect on the distribution of forces. We neglected that member CD is a two-force member and therefore would have no horizontal contribution at the reaction. And we neglected the pins at B, C, and D. So, it could be reasonable that our approximate answers were so different because we failed to consider all of those three things. But we still could have a reasonable answer now. So now let's go back and review the process we followed. In step 1, we approximated the solution so that we would have something to compare to at the end. We made some crude assumptions. One, that each horizontal reaction would share equally the lateral load, and then we also assumed that the structure would act like a box on 2 vertical supports, and so we could calculate the vertical reactions. In step 2, we divided the structure into its 3 members so that we could see all of the forces we would need to calculate, and in step 3 we confirmed that it is a determinate structure and it is stable. In step 4, we started by drawing a free body diagram of member CD, finding that the horizontal components were 0. Then we looked at member BC, found CY, which we moved over to our previous free body and found the vertical reaction at D. And then we found BX and BY. And then continued step 4 by looking at member AB. We had all of our internal forces from the previous free bodies, the lateral applied load, and we found each of the 3 reactions at A. Then step 5, we go back and compare the reactions we calculated with the approximation. We found that we got our order of magnitudes to check out, but the distribution of forces didn't match our approximation very well. So you always have to ask the question, why? Is it due to an error, or is it due to poor assumptions? And in this case, it turned out to be due to poor assumptions. We had ignored the moment reaction at A, we had ignored that member CD was a 2-force member, we had ignored the effect of the pins on the behavior of the structure. So our reactions that we calculated appear to be reasonable, even though the magnitudes don't match closely with the approximation, because the order of magnitude checks out and our assumptions were fairly crude. Well done.